Have you ever looked at a brick wall and thought about what it's really made of, not just bricks and cement, but way down at the tiniest level? What if we keep zooming in until we reach the smallest unit of matter? Well, just like a building is made from bricks, all matter is made up of atoms, the tiniest units that still retain the identity of an element. Atoms are the basic building blocks of everything, whether it's the air you breathe, the water you drink, or the phone you're holding. Definition: an atom is the smallest particle of an element that retains all its chemical properties. And they are unbelievably small. Millions of atoms stacked on top of each other would make a layer no thicker than this sheet of paper. We measure atomic size in nanometers, where 1 nanometer equals 1 billionth of a meter, or 10 to the power minus 9 meters. Alright, let's get a sense of scale. Imagine a grain of sand, already pretty tiny, right? Now compare that to a hydrogen atom, which is almost a million times smaller. Atomic radii vary, but most lie between 0.1 and 0.5 nanometers. That's 0.0000000001 meters. In scientific notation, that's 10 to the power minus 10 meters. Here's how their sizes compare. A hydrogen atom measures approximately 10 to the power of minus 10 meters. A water molecule is about 10 to the power of minus 9 meters. A red blood cell is roughly 10 to the power of minus 6 meters. And a grain of sand is around 10 to the power of minus 4 meters. As you can hear, the jump in scale from atoms to visible matter is enormous. So yes, atoms are mind-blowingly small, but their structure and behavior determine the entire chemistry of matter. Now that we know atoms exist, how do we write or represent them? Let's rewind to the early 1800s. John Dalton proposed a brilliant idea: use symbols to represent atoms of different elements. Not only would this save time, but it also gave atoms a visual identity. For example, Dalton used a simple circle for hydrogen and different patterns for others. Later, a more practical system came, using one or two letters from the element's name. This is what we use today. The rule is, first letter is uppercase, like H for hydrogen or O for oxygen. If there's a second letter, it's lowercase, like He for helium or Na for sodium. These symbols are now internationally accepted and used in all chemical equations and data tables. Ever wonder why sodium is written as Na instead of SO, or why potassium is K? Well, that's because some chemical symbols come from Latin names: sodium, Na, from natrium, potassium, K, from kalium, iron, Fe, from ferrum. Other symbols are simply derived from the English name, like C for carbon and Cl for chlorine. And it's important to note, A, small l, is for aluminium, not A, capital L. C, small o, is cobalt, not C, capital O, which stands for carbon monoxide. These symbols aren't just shorthand, they carry meaning. Memorizing them helps us write chemical equations with clarity and accuracy. Let's talk about weight, not of people, but of atoms. Dalton's theory suggested that each atom has a fixed atomic mass, but because atoms are too tiny to weigh directly, scientists created a clever workaround: use relative mass. Today, we use a unit called the atomic mass unit, or U. One atomic mass unit is defined as 1/12 the mass of a carbon-12 atom. Let's take carbon monoxide, a compound made of carbon and oxygen. Experiments show that 3 grams of carbon react with 4 grams of oxygen, so carbon and oxygen combine in a 3 to 4 mass ratio. This relative system helps us assign values like hydrogen, 1 atomic mass unit; carbon, 12 atomic mass unit; oxygen, 16 atomic mass unit. Visualize it like this: a fruit seller doesn't have a scale, so he uses a piece of watermelon as a reference to measure other pieces. That's exactly what scientists do with carbon-12. Using the atomic mass unit, we can now compare and list the masses of atoms across the periodic table. Here are some examples. Hydrogen equals 1 atomic mass unit, oxygen equals 16 atomic mass unit, sodium equals 23 atomic mass unit, chlorine equals 35.5 atomic mass unit, calcium equals 40 atomic mass unit. These masses help us predict how much of one element will react with another and are the backbone of chemical equations. Imagine trying to cook without knowing the exact quantity of ingredients. Chemistry without atomic mass would be just as chaotic. So here's a question: if atoms are so small, do they just float around on their own? In most cases, no. Atoms rarely exist independently. Instead, they combine to form larger, stable units. For example, they form molecules like O2, which is oxygen gas, or H2O, which is water. Or they form ions, such as Na+, which is a sodium ion, and Cl-, which is a chloride ion. These groupings of molecules and ions make matter visible and tangible, whether it's the sugar in your tea, the carbon dioxide in the air, or the salt on your food. Everything is made of collections of atoms bonded together, and it's this ability to combine, to cluster into larger structures, that allows us to see, touch, and interact with chemical substances in our daily lives. So, let's quickly revise what we've learned about atoms. Atoms are the tiniest units of matter, the invisible bricks of our physical world. We represent them using internationally accepted symbols like H for hydrogen or Fe for iron. Each atom has a specific atomic mass, measured in atomic mass units, where one atomic mass unit equals 1/12 the mass of a carbon 12 atom. And while atoms may be small, they're never alone. They join to form molecules and ions, which then make up everything around us. I hope this session helped you realize that understanding atoms is like unlocking the grammar of chemistry. It gives meaning to every reaction and every compound. Catch you in the next class with more molecule magic and real world chemistry.